It's pleasure to have Robert here. Robert is, has been working on many different topics, including quantum machine learning. And today he will talk about how to, learn quantum processes efficiently. And I think currently he's at Caltech, and he might be looking for jobs next, I believe. Or might already have one. And so I like to keep the session interactive. It would be nice if more people turn on their camera so that, it feels more like in person. And yeah, so, and would you like to take questions in between, Robert, or?
Yeah, that'll be nice.
Okay. So please feel free to, unmute yourself and ask if you don't get something. And Robert, could you start the screen sharing?
Yeah.
Okay. So yeah, the stage is yours.
Thank you. Thank you for the introduction. So I'm Robert, and today I'll be talking about learning to predict arbitrary quantum processes. It's been a while for Zoom meetings for me. I've been giving mostly in-person talks, but it's nice to give Zoom meetings again. And for today's talk, it will be a joint work with Hsin-Yuan and John Preskill. And also, please feel free to just ask questions in the middle if there's something you would like to know about. So recently, we've seen a lot of progress in how to efficiently learn about quantum states. Say, in the context of shadow tomography, we try to predict observables in quantum states very efficiently. However, there's much more limited progress in understanding how to design computationally efficient algorithms for learning to predict quantum circuits or quantum processes. So that will be today's topic, where we assume that there are some high complexity quantum process that might arise in certain natural settings. It could be in a quantum device. It could be some dynamics in a non-equilibrium quantum matter. It might be some catalytical process, or even more ambitiously, maybe processes that are happening in drugs. And the goal that we would like to do is to be able to predict what happens inside this quantum process using very few amount of experiments and computational power. More precisely, we're going to look at the following abstract problem, which captures various different problems of interest, where we wanted to focus on training an ML model that can learn and predict the following function. So the function takes in two objects. The first is an input quantum state and also an observable O. And the goal of the model is to predict what happens after we evolve these input state by some unknown quantum process, or people also know as CPT maps, and then measure the observable on the output. So note that such a function is very general. It includes any function that's computable by a quantum computer, even those that requires exponential time. So this is just the general setting that we're going to be looking at. In general, computing such function is going to be pretty hard. So some examples that lies into this include, say, we would like to train a model so that one could predict outcomes of physical experiments. In this case, the initial state would be some input. E would be the physical process that happens in an experiment, and O would be some measurements that the scientist does. Another example that appears in quantum machine learning is in training quantum neural network, where this unknown CPT map would now be within some manifold, basically some parameterized quantum circuit or some other manifold, which corresponds to the thing we would like to learn. Rho would be the input encoding some classical, it would be an input state that encodes some classical input X. And then O would be, say, some fixed observable, such as measuring the first qubit in Z1. Another example that have also been recently studied is in trying to speed up complex quantum dynamics. Basically, we want to learn an ML model so that it can predict outcome of some, say, quantum evolution faster than the quantum evolution itself. For example, maybe there exists some more low complexity model in performing the prediction, And then in that case, we hope the ML model is able to find such a low complexity model and predict it. So just to summarize the goal is the following, is that we're given some n-qubit CPT map E that represents a high complexity quantum process. So that's given by this block here. We don't know what it is, some high complexity quantum process. We perform a set of experiments on this quantum process in order to generate some classical data set. We feed that into a classical machine, which produces a learned model, such that when we would like to predict the output of some input, what we would do is we will just use this low complexity learned model to make the prediction. So for example, maybe we specify what are the properties of the input state, feed it into the learned model, and then the learned model will produce properties of the output state. So that is the goal of today's talk. And if there's any question, feel free to just raise it at the moment.
So when you say like learning the process, like here,
Yeah.
are you saying that, like approximation of the CPTP map in terms of, certain cross operators, let's say a fewer number of cross operators, which are classically representable?
So yeah, so for example, that could be an approach for doing it, but at the moment, this is still kind of high level. The classical machine can do all kinds of things, including what you suggested, maybe learn some kind of a restricted cross operator in order to approximate it. But it could also utilize all kinds of other different representation. Particularly in this talk, I'm going to talk about one representation for representing it, which is different from just cross operator representation. But one could think more broadly on how to do this. So for example, in the more restricted case, we can say we wanted to learn it in terms of diamond distance, then we know that this is very hard. This is exponentially hard, and one cannot do better. So here, what we would like to really do is that maybe we don't want diamond distance, because diamond distance means for all possible input states, including ones that are non-physical, we would be able to predict all possible observable, including those observables that are not physically relevant. So we wanted something that, some approximation that's more physically relevant, but at the same time also possibly easier to achieve. So we would like to understand what kind of approximation would that be, and what kind of algorithm will be able to achieve that. So that's part of the goal on here.
And you require the map to be like CPTP? I mean,
so the thing we're trying to learn is a CPT map, but the learned model can be anything. It can just be like some classical algorithm that doesn't try to project back to a CPTP map, because that projection itself can cause a lot of trouble. For example, in shadow tomography, in classical shadow, the representation that one learns is actually not a quantum state. And that's actually very useful. If you try to map that representation back to a quantum state, there are actually works that show that performance get much worse. So being able to go out of CPT map realm is actually quite useful in learning, or could be quite useful. And here's the overview for the content. First, I will talk about a classical version of the quantum problem, and then I will talk about a restricted version, and finally, I would go back to the original problem. So let's begin with the classical version. But here's a corresponding classical problem. We're given some unknown classical Boolean circuit C that maps n bits to n bits. So in this case, the input is not an n-qubit state, but an n-bit classical string. And say, for example, for the output, we don't care about some arbitrary observable. We just care about a very simple one that is measuring Z1 on the first bit. And that would just correspond to predicting the first output bit of some classical circuit C. You can also write it out more quantumly as this formula shown here, where we just treat the classical Boolean circuit C as a CPTP map. So for this problem, we can look at both the worst case and the average case. So note that such a function fc is equivalent to an exponentially long vector without any structure in it. So if we would like to learn a model h of x such that for all possible input, the model prediction and the true function differs by, say, at most 0.5 in terms of square error, then in this case, what one could show is that because there is no structure in it, we must query FC of x for all possible input x, resulting in a query complexity that scales exponentially in this input size. So that's the worst case situation, which is pretty bad. But things are not much easier when we focus on average case hardness. So let's say instead of trying to learn a model that is correct for all possible input, we just try to learn a model h of x such that, say, when we randomly sample a new input x, on average, it's close to the true function fc of x. In this case, one basically can show that you still need to query at least half of all possible input in order to achieve this, resulting in a query complexity that's, again, exponential in the input size. So as we can see for the classical version of the problem, both the worst case and the average case are pretty hard. They're both exponentially hard. And furthermore, in recent work around 4 years ago, it was also shown that if we place restriction on what this classical circuit is, it can still be very hard. Say, for example, this is a shallow classical circuit. Then one can show that getting a good average prediction error, like an average over x, the square error is less than 0.5. It's still computationally hard, even when it's like constant depths, such as what people call TC0. So these are essentially Boolean analogs of constant depth neural networks.
So let's say you're talking about okay. So let's say normally, let's say when people talk about constant depth circuit, they talk about NC0 and in the quantum case QNC0. That's not hard, right?
Yes, NC0, that's easy. But there's a class of version also known as, so there's actually a few one that people have defined that's people call constant depths. First is NC0, that's geometrically local gates. The second one is called AC0, where we have AND gates and OR gates with unbounded fan-in. So we can take a bunch of many bits and then take the end of it. So that's called AC0. That's also hard. And then for TC0, that's when you have majority gate. That is, you can think of it like a neural network, where you kind of do a majority vote to decide whether you activate or not.
There is this so like NC0. So there is this hierarchy, right? NC hierarchy and the AC hierarchy. And the AC is sandwiched between NC, right? So NC0 is like, inside AC1, AC0, which is in NC1. So let's take NC1, that will be log depth. So
yeah, that will be hard because it contains AC0.
I see.
Yeah, so there's NC0 containing AC0, containing TC0, which is containing NC1, and then so on, which is containing AC1 and so on. So it's known that for NC0, it's easy, but AC0, that's hard.
I see.
Yeah. And we also know, like, there's a paper by Robin Kothari and others that show that if you have QNC0, that's actually, it can be exponentially more powerful than AC0. So that result is also.
I think you mean FQNC0, because QNC0 is equal to NC0. Like the moment you have the relational analog.
Yes, a relation. Yes, I should say it's with the F. Yeah, so as we can see, this problem, when we define it in some classical, like consider a natural classical analog of it, it's very hard. And now what we'd like to do is to look at some restricted version of the quantum problem and see how that looks. So recall that in the classical problem, the input, if we draw it based on block sphere, looks like this, just a bunch of ups, downs, and so on, that correspond to the input bit string. And we just wanted to predict Z1 for the first qubit. So we know that this is hard. However, we can ask the following. What about the quantum problem where the input is, instead of just 0 and 1, it's now all possible product states now with on the block sphere? Is this problem even harder? So in this case, we're going to look at an observable O, which is just a Heisenberg evolution of Z1 under this unknown quantum process. So this observable O serves as a similar role as this FC function that we looked at earlier. In particular, we're going to look at the following classical data set, where essentially each repetition, we just prepare some random product state, and then we evolve it under this quantum process, and then measure in the first qubit under the Z basis. So now this is a classical data set that tells us about this Heisenberg evolution of Z1 under the unknown process O. So we have all these product states being mapped to a real value YL, which is either +1 or -1, with the expectation value equal to psi L O psi L. So now the prediction task for this restricted quantum problem is that we can learn from the classical data set, which tells us how, for different random product state, the evolution acts on it. We would like to know if, when we are given a new state, psi, another product state, whether we can predict psi O psi accurately. So recall that psi O psi is basically, we take the new state, evolve under quantum process, and then measure Z1. And also, one can also think a little bit about how this relates back to the classical problem. In the classical problem that we just talked about, we should think of O as a diagonal observable. So it's a diagonal matrix. Each entry is like +1 or -1. So first, we can look at the worst case hardness. Say the goal is to learn some model, H, such that given any product state, we will be able to predict the true value up to, say, 0.5 error. Then this problem, under worst case, is at least as hard as the classical problem that we just looked at under worst case, because we can just pick psi to be the classical bit string. So in this case, the query complexity will just directly port over, and it will be at least exponential in system size. On the other hand, we can also look at the average case. So in this case, instead of trying to predict accurately for all possible product state, we just try to predict accurately for most of product state. That is, we take some expectation value over product states, and then say the average error is less than 0.5. And the question is this problem whether this problem still exponentially hard? So recall that in the classical problem, this is still exponentially hard. However, what's quite interesting is that in this case, when the input is considered to be quantum state, the answer turns out to be no. And one can actually solve this problem in quasi-polynomial time.
This is nice. Like, can you go back? So basically, are you saying? Yeah. So the quantity O that you are measuring, it corresponds to measurement of you perform a process, and then after that you measure just a single qubit, right? Just a single qubit. Yeah. So in the classical case, you will be interested in some Boolean circuit, right?
Yes. One replace the quantum process by a Boolean circuit, and say we look at the first output bit.
Yeah. And classically, basically, you're saying that the worst case as well as average case both are hard. Quantumly, the worst case is hard, but the average case is not so hard. Nice.
Yes.
So let's say, Robert, let's say here, if you, instead of decision problem kind of setup, if I get into a relational problem, like let's say if I am interested in multiple qubits, let's say Z1, Z2, Zk, I'm not sure whether you looked at that, but any intuition, whether it will still remain quantumly,
Yeah, so basically, I would talk about it slightly later, but for any observable, it would be easy. Like any observable that you measure, it could be, say, Z1 tensor, Z2 tensor, Z3 tensor, Z10 tensor, some many other things. It would all still be the same. It would still be quasi-polynomially easy. So that we know, but that's still more like a kind of the output is a real value, rather than like a sampling problem. So to be honest, I don't really know for sampling what would happen. Say we measure it, and we would like to be able to produce some probability distribution that kind of is close to the true one in trace distance, for example. Then I'm not sure.
Nice.
on that complexity. But if it's just some other observable, not Z1, but some more complicated one, then it's still quasi-polynomial sign. Yeah, and now I'd like to talk about what's the main idea behind this. It's actually a very simple idea called low weight approximation. So we call that the observable O is the one that we're looking at. And we can always write out observable in terms of the Pauli basis. That looks like this. And the low weight approximation, as we define in our work, is that we only look at Pauli operator that acts on few qubits, acts on, say, up to k qubits. Then we can also define an observable, which we call O low, which is the lower approximation to O, as truncating away all the other terms that consider high weight Pauli. So we only can reduce it to consider low weight Pauli. Then a lemma that was shown in our work is the following low weight approximation lemma, which says that on average for product states, the difference between any observable O and its low weight approximation decays exponentially fast based on the truncation. So if you truncate at k at certain value, like log 1/epsilon, then the error will be epsilon. So it's a very fast decay in terms of the weight that we truncate at. So another way to think about this is that it means for most of the product state psi, psi O psi is roughly equal to psi O low psi. And this is a key difference that separates between the quantum case and the classical case. In a quantum case, when we average over these product states, we see this decay. But in the classical case, when we average over just bit strings, we actually don't have this decay. We can have k being very, very large, and yet the difference between them is still of order 1. So that's the main difference that separates between the quantum case and the classical case for this problem. Another way to think about this is that in the classical case, all of these inputs are perfectly distinguishable. You can, different bit strings are orthogonal to one another. But in the quantum case, it's not. For all of these different quantum products, they actually have quite a bit of overlap with one another. And this overlap allows one to reason about what other things are, like other states are, based on existing results. So these quantum state inputs are not perfectly distinguishable, which actually makes the problem easier. So now, given this observation, given this lemma, a basic idea that one could use for the ML algorithm is the following. We just try to learn this low weight observable O low for some small value k. And the way to learn it is using essentially the following Fourier transform based idea, where one can show that alpha p can be obtained by using this expectation value. So one could also just replace the expectation value with, and then one essentially shows that when we have this averaging over the classical data set, it will concentrate to its expectation value just by simple law of large number. And hence we can get a good estimate for what alpha p is. However, there's still a challenge in understanding how fast the concentration happens. So we know that there's this equality, which is true on expectation over this classical data set, like how it's being generated, like the quantum measurements, and also how the random product state is being sampled. However, in general, there would be fluctuations around the true value if we throw away the expectation value. However, since we're doing averaging, there will be nice concentration, and we would like to understand how fast does it concentrate into the true observable O low, which corresponds to how big the data set size n has to be. In order to answer this question, we're going to do a detour into a different problem. Particularly by going through a detour, we're going to find that actually the size of the data set can be very small, only logarithmic in the system size. And to do that, we are going to do the following. So we're going to look at a completely different question called optimizing quantum Hamiltonian. I think the question should be pretty straightforward for most people, is that we're given some n-qubit k local Hamiltonian H, And what we like to do is to find a state psi that either maximizes or minimizes the expectation value of the Hamiltonian edge. And in particular, what we would like to do is to have an algorithm that gives a guarantee on the optimized energy value based on the description of the Hamiltonian. So this part is going to be a bit more complicated, but basically we showed that we need to define a notion called the expansion property of the Hamiltonian edge. The idea is to sort of understand what's the connectivity in edge. Particularly, we would have an expansion coefficient and also an expansion dimension. Expansion dimension is the more crucial one. The coefficient is just some constant value. But the idea is that if you have an expansion dimension of d, then for every size d region that we consider, for example, size 2 region, in the n-qubit state, so say we just randomly pick some 2 qubit, the number of Pauli operator that's non-zero with non-zero coefficient, such that it's being dominated by this R or dominates R, meaning that, like for example, like if the Pauli operator corresponds to this one, it's X on this qubit, then we would count it. And another Pauli operator, such as this one, which is Z and Z here, we would also count that. And another one that we would count is something like this. However, say the Pauli operator X on here, and then Y on here, but then identity on here, then we will not count that. So it kind of captures the structure of the Hamiltonian. But to understand it a little bit better, here are some examples. So suppose that we have a geometrically local Hamiltonian, then we can show that the expansion dimension is just 1. And the coefficient CE would just be some constant. On the other hand, if we have a general K local Hamiltonian, meaning that there are interaction terms between every K qubit, in this case, the dimension would be K, and the expansion coefficient would be 4 to the K. Another example is, say, we have a 2-body Hamiltonian of degree D, meaning that for each qubit, it's only being acted on by at most D terms in the Hamiltonian. Then we would have something like DE, the expansion dimension is 1, the CE is 16D. So it's a form of how well connected the Hamiltonian is in the entire n-qubit system that defines this expansion property. And when DE is higher, it's more connected. And then for things that are not very connected, like all these things that are like geometrically local, like a 1D chain, 2D lattice, 3D lattice, they all have dimension equal to 1. And now the theorem essentially says that given some Hamiltonian edge with expansion coefficient CE and dimension DE, there's a way that one could design an algorithm that finds a maximizing product state or a minimizing product state. So I try to find a psi that maximizes the energy or minimizes the energy with an advantage that corresponds to this term. It's a little bit complicated, but the key parts that one should look at is essentially this definition of R. So R corresponds to this term, 2DE over DE plus 1, which when DE becomes higher and higher, R would be closer to 2. And say when DE equals to 1, R would be equal to 1. So when R equal to 1, this becomes just a 1 norm. But if it's close to 2, then it becomes a Euclidean norm. So we also know that when we have a vector, the 1 norm can be much, much bigger than the 2 norm. So it means that the advantage that one could gain, for example, we can get a much higher energy if R is closer to 1 instead of 2. But if it's 2, then the advantage over just a purely random state will become much smaller. That's kind of the key insights this term. The other parts are just, one can think of it as just some constant that are in front. But the key part is this R factor that will become more relevant in proving the sample complexity bound later. And if one compares this to other existing results for optimizing Hamiltonians, this result improved upon them. And it could be quite, the improvement can be quite very significant in certain regimes. In particular, for the regimes that we care about, one needs a theorem like this in order to achieve the final guarantee.
So basically, like before you talked about like for any observable, so you can write it in the Pauli basis, right?
Yeah.
And then you said that, like we would like to truncate it to Pauli basis, which has, like Pauli terms which have a smaller weight. And,
Yes.
and you had this result where you said that, yeah, I mean, if the truncation, like order is k, then it will go like 1/3 to the power k or something, the difference between the actual value and the average value. And now
Yes.
you ask the question that what if the O that I'm interested in is Hamiltonian of a system? And
Yes.
Hamiltonian is an observable, and I can write Hamiltonian as sum over Pauli. And then you're saying that, let's say if I want to learn, and basically you had this approach to learn alpha p. So let's say if I replace my O by Hamiltonian, then it's nothing but Hamiltonian learning problem. So like given some input, you want to learn the coefficient. So then you switched gears and you said that, okay, let's look at the Hamiltonian.
Yes.
And in the case of Hamiltonian, you said that, like, given some connection properties and so on, like if let's say this DE is such that, let's say if DE is large, then my R will be close to 1. And in that case,
it would be close to 2. And then the improvement over a purely random state in terms of like we wanted to maximize or minimize the energy, the improvement will be much smaller, right?
Yeah.
Because the norm is much smaller than one norm.
So you want
especially
DE
for high-dimensional
to be, so you want DE to be what? Like smaller?
Yes.
Correct. Okay.
Yeah.
So then and then you got this Hamiltonian learning, like algorithm, and you're saying that the algorithm that you got is like improves over the other.
This is actually not a Hamiltonian learning problem, but more like a Hamiltonian optimization. So say we wanted to find a low energy state or a high energy state. So
finding I thought, like when you were trying to find the coefficients alpha p. Okay.
Yeah, so that's why I switched gears. So that's what we would like to do here. But then in order to get this kind of magical logarithmic in unbound, we actually need some additional tool coming from a very, very different field based on optimizing quantum Hamiltonian rather than learning quantum Hamiltonians.
I see.
Yeah, so it's kind of a jump. Yeah, the task here is, I think, yeah, it's pretty natural. We're given some Hamiltonian edge and we would like to find some state that maximizes the energy or minimizes the energy.
I see.
Yeah, so that's a very different task. So it's not about trying to learn what the Hamiltonian is, but about trying to optimize it. So like in finding ground state or in quantum optimization and so on.
Yeah.
Okay. Yeah, it is in this context that we improve. It's improving upon optimization results rather than upon Hamiltonian learning results. And now I'd just like to give a brief idea for how the algorithm looks. So the algorithm here is the following. We are going to originally the Hamiltonian has multiple different weights, and we're going to take a slice that has the largest value of alpha p. So we can consider p equal to, like the weight of p equal to 1, 2, 3, and so on up to k. We're just going to pick one with the largest value. And then what we're going to do is we're going to form multiple copies of the n-qubit system, particular k copies. We're going to take random product states for the first few copies, except for the last one. And then what we're going to do is we're going to take this Hamiltonian edge, lift it to this bigger system. So originally this Hamiltonian is an n-qubit system. We now lift it to a n-k-qubit system. The lifting works as follows. So in particular, for each of these Pauli terms, we're just going to define what we call polarization of p. And then the Hamiltonian itself would just be the linear combination of these. And now I would like to talk a bit about what the polarization means. Suppose that we have a Pauli term that is ZXYII. Then the polarization is the average of the following Pauli terms. Z here, X here, and Y here, everything else I, plus Z here, X and Y, ZXY, ZXY, this and this. Basically all possible permutation over this K copy system. And that's basically what we call polarization. What we're going to then do is we're going to then look at this polarized version of Hamiltonian, which is now a Hamiltonian over this bigger system. Originally, the Hamiltonian is over n-qubit, so just a single slice. Now we're having a Hamiltonian that is over the whole thing. And we already selected the other replicas by just randomly choosing a product state. What we can show is that by the definition of this polarization, one can actually optimize over the last replica exactly. We can actually find the exact optimal product state in the final replica that maximizes this polarization of edge. And then what we were going to do is we have found the maximized version, that's called the red ones. We're just going to combine them into an n-qubit system. So originally it's these nk qubit system. We're going to smash them together, and now they're an n-qubit system. We're going to combine them using some random weighted sum, and that gives the state. So let's say these are the states. And yeah, that's the basic algorithm for optimization, which we found to be quite different from how previous optimization algorithm works for optimizing quantum Hamiltonians. And using this optimization algorithm, one gets the following theorem. Now here's another interlude where we're going to utilize this optimization algorithm to prove an inequality, which is essentially the quantum version of the Bohnenblust-Hille inequality, which is an important inequality in classical harmonic analysis. Essentially, the theorem states the following. Suppose we have an observable O, which is only have weight up to K. One should think of this O as the low-rank approximation. And suppose that this observable has an expansion coefficient CE and a dimension dE, then we can prove that the spectral norm of O, which in most general cases, one should often just say the spectral norm of O is upper bounded by 1, because we say the observable only takes value between -1 to 1. Then in this case, we have this constant value with upper bound, essentially the LR norm of this alpha p coefficient. In particular, this R value would be 2dE over dE plus 1, which is in between 1 and 2. So for example, if dE is like 1, then this is again 1. So the 1 norm of alpha p would be upper bounded. Or if d is slightly larger, then the R norm, where R is now closer to 2, will be upper bounded. And to prove this theorem, essentially, we just take the guarantee from the algorithm, utilize the fact that the spectral norm upper bounds this energy value, where the psi is the state found by the optimization algorithm, and then together we will immediately get the theorem. It's pretty straightforward. So let's look at again what this theorem becomes in different cases. Suppose that the observable can be written as the sum of geometrically local term. Then previously, we've seen that the dimension will be equal to 1, and the coefficient will be a constant. If we plug everything back into this theorem, then what we get is that the 1 norm of these alpha p coefficient will be upper bounded by the spectral norm of O, which in general, if we consider some constant spectral norm, we have that this 1 norm of alpha p would be bounded by a constant, which essentially means that the observable written in terms of its Pauli decomposition will be sparse. So if people are familiar with, say, compressed sensing and so on, then whenever we have a 1 norm bound in things, then suddenly things becomes much easier to learn. So here we're looking at this observable O that we're trying to learn, like going back to our original task. And now if we have this additional inequality at hand, that one norm is actually bounded, then suddenly learning becomes very, very efficient. And that's essentially why we need this Bohnenblust-Hille inequality. Another example is when the observable is more general, it's just a sum of k body terms or k local terms. In this case, the dimension dE would be equal to k. And what we would get is that if we treat the alpha p coefficient as a long vector, then it's 2k over k plus 1, which is a value that's less than 2. It will be upper bounded by the spectral norm of O. And this is the quantum analog of the Bohnenblust-Hille inequality, which tells us about what kind of constraint we can actually place on the observable, on the Pauli coefficient of an observable, which is something, again, quite very useful, because when we have these constraints on the observable, we know that it's more restricted than, say, we only have L2 norm constraint. If you only have an L2 norm constraint, like replacing this number by 2, then there's not really a sparsity in the vector. But if we have this R norm bound, or 2k over k plus 1 norm bound, then suddenly it says that the alpha vector is quite sparse. And when it's sparse, it becomes much easier to learn. So now we can finally go back to our original problem. So recall that we have this quantum problem. We would like to be able to predict for some input state what's the output after some high complexity evolution. And recall that we have this basic idea, which is we try to learn the low weight truncation, O low. We can learn them, each of the coefficient, using the Fourier transformation. However, we would like to know how many data do we need in order to be able to get a good estimate for this low weight observable. That is, how large should the data size be? So now what the Bohnenblust-Hille inequality tells us is that it's this second insight. The first insight is we just learned this truncation. The second insight is that these Pauli coefficient in these low weight observable is going to be approximately sparse because of this inequality, which says that some R norm, where R is less than 2, for this vector alpha, it will be upper bounded by some number that's not too large. As long as, say, if k is like not too large, then 2 to the order k log k would not be very large. And then it would be much more bounded. And when it's much more bounded, we can learn it very efficiently. So such a sparsity idea is also used in classical learning theory more recently. So now together, the ML algorithm is the following. Actually, it's very, very simple. For each of the low weight terms P, we just use the Fourier transformation identity to find an approximation for alpha P, called alpha P hat. And because when the vector is sparse, we know that there's going to be a large number that are very close to 0. And for those large number, we can just set them to 0. So if we found that alpha P hat is quite small, we just set it directly to 0. And the reason for doing that is because originally in the original problem, when we do this, there's going to be a lot of fluctuation. And since there's many, many terms, the fluctuation can be quite large when we added them all together in creating this final learned observable O hat low. However, if we found out there are certain values that are pretty small and set them to 0, the noise get canceled. We just throw away the noise. And by doing that step, it becomes very easy. The noise becomes much smaller. And now it will be much more easier to learn what O low is, the low weight approximation to the unknown observable. So now using all of these together, what we get is the following statement. For any small constant epsilon, given a training set size of order log in a system size, we can show that the prediction error is upper bounded by epsilon times the spectral norm of the low weight observable O low. More precisely, or I should say, the difference between the learned one and the true O low is this. And now also recall that the low weight approximation is close to the true observable O, which can be much, much more complicated. Together, what we get is this inequality, which again says that a training set size of log n allows one to get a prediction error of roughly epsilon plus epsilon prime times the spectral norm of the low weight observable. And now we can also take into account what's the scaling for epsilon and epsilon prime, and we essentially see that it's exponential in the logarithm. So that's why it's a quasi-polynomial scaling in terms of the learning complexity and also the computational complexity. So together, what we see is that in the original classical problem, when we have inputs being bit strings, that's exponentially hard in both worst case and average case. Now in the quantum problem, the worst case is still very hard, but the average case becomes quasi-polynomially easy. And now we can go back to the real original quantum problem, where the goal is to be able to predict much more richer class of properties on the output state, and also work under richer class of input states, not just product states. So now, instead of having this classical data set that we just measure a single qubit at the end, like here, we consider randomized measurements on all qubits after the quantum process. And one could think of this as essentially the classical shadow version, the quantum process version of classical shadow tomography. And the classical data set now would look like this. We have a bunch of different random product state input. And then after measurements, we would get some also random product state. For example, if we measure in the computational basis, then the output will be like 0 or 1. If we measure in the x basis, it would be plus or minus and so on. So that's the classical data set that we get. And now, given this classical data set, what we would like to do is to be able to make a prediction. So we have some input state rho, evolve under quantum process, and then measure it with some observable B with a spectral norm bounded by 1. So to do this, what we're going to do is we're going to take the classical data set and take the knowledge of the observable to create a new classical data set, essentially using classical shadow tomography for quantum states, where in the new classical data set, we still have a bunch of product state input, and the output is now a real value with the property that it would be equal to when we actually measure these observable after the evolution. Recall that right now, after the evolution, we're just doing randomized measurement. But then using the basic idea of classical shadow, one can then combine the randomized measurement outcome with some observable and essentially turn the classical data set into a new one where the output is as if we have measured the observable B in the first place. So that's what happens in the first step. So here it's a little bit complicated, but basically.
Sorry, I think I lost. Yeah, I'm not able to follow. So basically, you're saying that so there's this shadow technique where you you perform measurement in random basis and get information about the state. Now you have some initial state and it goes through some quantum process. And after it has gone through the process, you would want to learn the property of the evolved state, basically.
Yes.
And in the average case. And so basically you are saying that you would like to just add one extra layer of random unitaries at the end, and basically use it to learn the. So do you actually send the evolved state through the quantum process? So basically you assume that you have copies of the evolved state and you have copies of the input state, right?
So the input states are just chosen randomly. So we choose them randomly. They're just random product state. And then after evolution, we just measure in the random basis.
So what I'm confused that, let's say if somebody gives you the evolved state, then you can just do shadow tomography, right? And you can just learn, right? So the challenge would be to just given the input state and maybe some description of the quantum process. you will have to.
Yeah. So right now we don't know what the quantum process is. So yes, we're trying to learn some description of the quantum process.
Correct. So like that somebody gives you the output state also, like the what? Like
No. So that's what we're trying to predict.
So if you are not given the description of the process and you are not given the output state, then like I'm a bit confused.
Yeah.
You're only given input, then how can you?
Sorry. We're given some. So first there's a training part where we're given different input as well as the corresponding output. So I guess you're asking about that part.
Yeah, I mean like that part, and then like so you learn the description of the quantum process, I believe. Then.
Yes, from these input output pairs.
I see. So you have these input output pairs using which you learn the description of the quantum process.
Yes.
And once you learn the quantum process, basically you are saying that I will get the output state using my input state, and on the output state I will perform the shadow.
Yes, that's one way to think about it. But I should say it's all combined. So together we're both performing shadow on the output state as well as predicting the output combined.
I see.
We don't really generate the output state because that's a very hard task. So we bypass it and directly generate the property.
I see.
On the output state, yeah.
So you're saying that you learn the description of the process and use that description to directly learn the properties of the output state, and not that. So on what do you perform the shadow? Like let's say if you do not generate the output state, like where is the shadow actually performed?
Oh, the shadow is performed on the training data part. So I turned the whole training data to classical.
I see.
Yeah. So originally it would be input output quantum states, but that's quantum, right? So we turn it into classical by doing shadow on the output state.
I see.
Yeah. So that's what this classical data set actually meant. And then from the classical data set, we try to predict, and we try to learn a description for this quantum process. And the description is implicit because all we're doing is we have an algorithm such that it will be able to predict the output property given some input state rho. So the output property is this B, and then the input state is rho.
I see. So basically the resource that you are using is this like the input and output states, like when which and you're saying that you don't need many input output pairs. I see.
Yes. Yeah. And the implicit algorithm is we take the classical shadow. We take the training data set, which contains different input state, as well as the classical shadow for the output state. And now what we do is we first turn it into another data set, which contains the input state, as well as a predicted observable value for the one we would like to predict. Because we never really measure B in the training set. We just measure these random things. So now we have to first do one step that turns it into a new data set where we kind of post-processingly do it so that we can pretend we actually have measured the observable O on the output state. So that's the first step. And now the second step is very similar to the previous problem that we just talked about, because now we just have some observable B, and then we can inverse evolve it under the quantum process E to obtain this observable O. And we also have this classical data set that tells us that for all of these different random product state, what's the estimate for an expectation value of the observable O. So that's essentially done by classical shadow. And then, so now it's almost back. The one last thing that was not there was previously we're just trying to predict the outcome for another random product state. So we're trained on random product states, and then we wanted to predict what happens for another random product state. But here, what we would like to do is to be able to predict some other general quantum state, like maybe rho is a highly entangled state, for example. And basically what we showed is the following. We showed that low-weight approximation also holds for other distributions. So not just for random product state, but it's for any distribution D over all possible quantum state rho, as long as D is flat under single qubit rotation. Meaning that if there's a probability of sampling a state rho, if we perform a unitary, like a single qubit unitary on one of the qubit, then that new state would also have an equal probability of being sampled. So for example, if we consider, say, rho to be some ground state or thermal state of a generic geometrically local Hamiltonian, it would correspond to a distribution D. Essentially, we showed that for these more general class of states, we still have low-weight approximation. It would still decay. It would not decay as fast. Previously, it's 3 to the k. Now it's only 1.5 to the k, because the state rho can be, say, highly entangled and things might be a bit more complicated. But in general, we still have this decay. And hence, we can use essentially the same algorithm as before to predict what happens for this state rho. So what we do is that we essentially learn a low-weight truncated version of the observable O, where O is just a Heisenberg evolution of the observable B that we wanted to predict under the unknown quantum process. And the algorithm is very simple. We just, to learn the low-weight approximation, we go through each low-weight term P, use the Fourier transform identity to get an estimate for the Pauli coefficient. And if it's small, we set it to 0, essentially using the Bohnenblust-Hille inequality. And then at the end, we would get the learned observable O hat low. And finally, we take this O hat low, apply onto the state rho that we want to predict, and we can show that the predicted value would be approximately equal to the true one. That is, if we really feed rho into this unknown quantum process and measure the observable B. So together, this is an ML algorithm that allows one to learn to predict the output property given some input states. And some of the surprising aspects of this algorithm is that we can actually predict n-qubit exponential size quantum circuit up to a constant relative error from only a logarithmic amount of samples. The algorithm is also computationally efficient. It's polynomial time if we focus on constant relative error, and quasi-polynomial time if we focus on a very small error. And furthermore, we've seen that after just learning from some random product states, the algorithm can actually learn to predict entangled state. So it has some stronger form of generalization. And finally, the entire learning algorithm can be done on a classical computer.
Sorry. So this part is confusing. So you're saying that so you can learn only on product states. It can predict on entangle. So like you overall, you don't need any entanglement in the process.
Yeah, no. That corresponds to essentially.
So can you let's say.
Yeah.
So you can simulate any CPTP map.
Yeah, but only on average. So like you have some distribution over input state, and then on average, I can only predict output properties. I cannot really produce the output state. It's properties on the output state, but not the output state itself in trace distance.
So think about, like let's think about like so yeah, so obviously, I mean, let's think about the average, stick with the average case only. And we have a BQP device, and we want to simulate it. Now you are saying this, that the whatever, like so basically the average case like property evaluation by a BQP device is something that can be dequantized.
Yeah. With the help of training data. So you need a training data.
You need, so does this mean that you need this? Can I think of the training data as some advice string?
Yes. Yes.
So basically, you are saying that P / maybe R poly includes like the average case. I mean, okay, one has to define the classes like
it's average case, so it's a little bit it's different, right? So it's not BQP, but some
So but this average case, like whatever BQP, like that's contained in P / poly.
Not quite, because it's quasi-polynomial time.
Quasi-polynomial.
Yeah. If we kind of extend it a little bit, quasi-polynomial, then yes.
I see. Okay, nice. Okay.
Yeah. So to conclude, in this work, we give a computationally efficient ML algorithm that can learn to predict the output of a quantum process with arbitrary high complexity. Particularly, I think one of the more positive spins on it is that it highlights the potential that ML models can predict outcomes of a very complicated quantum dynamics much faster than the quantum process itself. Like, for example, the quantum process might require huge amount of evolution time, like maybe because in nature, things happen very quickly. So it might actually already done a lot. But actually, when we train an ML model, we can learn to compress that very significantly by learning this low complexity model that's inherent in any quantum process, as we have shown. And that's it for the talk. Thank you so much for listening.
It's like if there are questions, please unmute yourself and ask. By the way, these DALI pictures are nice.
Yeah, I agree. I didn't do much work. It's really just by DALI.
Yeah.
Hello, Robert. I have a question to ask. If
Yeah.
you were to change the observable, then would you need to restart the entire training process, or could you do some form of transfer learning or something like that?
Yeah, that's a good question. So in a way, we are doing a restart, because as you can see, we are given this data set, and now given an observable, we generate a new data set. And then after generating a new data set, we essentially do the estimation, obtain this learned observable, and then put it onto the state row. So in a way, it is true that given any new observable B, we're going through everything again. So it might be possible that one could speed it up by doing some kind of transfer learning. For example, maybe these alpha P, where, like, for example, maybe for different B, B1, B2, B3, the set of Pauli operator P that would be set to 0 actually are very, very similar. Then in that case, we should just neglect them, right? Like we might want it to learn some meta model such that it learns to say, oh, we should skip this P because likely it will not contribute too much. And then that can make everything much, much faster. So which is what people want to do with transfer learning. So yes, so I think there are definitely opportunities to be explored there. I haven't really think hard about how that would look like, but it does seem reasonable that something like that could happen.
Thank you.
Hey, I do have one question.
Yeah.
So I'm just trying to think if your this low rank approximation this where you have the one norm of the alphas, low weight approximation, if this will carry over to the case when you have certain temporal structure on your CPTP map. So so if you're I'm not sure if you're aware of the quantum combs or process tensor structures. So I guess like it's more like when your CPTP map is composed of this unit, and the first layer is a unitary on first and second qubit. The second layer is on second and third qubit, and so on. yeah, just wondering if this will still hold in that case.
So here, like this lower approximation holds for any quantum process. So I would expect it to hold. I'm not entirely sure how the temporal correlation comes in. It seems like it's some kind of a restriction on how, from how you describe it, it sounds like some kind of restriction for how the quantum process actually looks like. But this result holds for any quantum process. So for those restricted quantum processes, it would still apply.
Yes, I'm just wondering if
Sorry.
the expansion of this like linear decomposition of this observable in terms of the polys, then I mean, like I'm not sure if that will, you can, you know, it must have some certain structure to that decomposition, but yeah, I'm just trying to think about how that comes into play there. But yeah.
But you know, I think once, like after, like, you know, Andrew, like, since talked about comps and all, like, so basically states are example of one comps, and the channels, they're example of two comps. But you can in general have super channels, we take channel as input, or you can have super duper channel and so on. So like people have generalized it to, you know, like k comps. So basically k plus one comp takes k comp as input. So for example, a 2 comp channel takes a state as input. So as of now, you know, like you have you know, basically shadow based learning for, let's say, k equal to 1 and k equal to 2 case. But one could think of what if, you know, like put in general k comps, what will you know, like how will you learn it? And in fact, you can experimentally implement super channels also, and in certain cases they make you know, like life easy, like, yeah. So
I see. That's interesting. Yeah, I haven't thought about, I didn't thought about that before.
So recently
the state case and the channel case are actually very different. Like in a state case, you get everything pretty good, but then in the channel case, you see that there are these quasi-polynomial factors that start to come in and so on. So they already differs quite a bit. So I'm not sure, like going upper, what would happen. Although my feeling is that it might be similar to the channel case, because I think the key difference is like the state case is more like just distribution and channel are more like function. But I think going even further up, it would also be more like just functions. So I would expect something similar might also happen, but I'm not sure. And another important thing is also for these, say you say k equal to 2 comps or 3, how one could properly, how one should define average case. I think that's also another question. I don't really know what's the right way of defining average case there, but yeah, but it does seems like it could be possible that with the right definition of average case, all of these things could generalize to higher.
So yeah, so recently I think, yeah, like, so there is like one of my colleagues here, Daxco, like, you know, we wrote one paper on channels, super channels, all those things. And I think he works on this shadows also. Like I think he worked on the classical shadows with noise. So
yes, several very nice papers.
Yeah. So I think one could think of generalization for, I don't know how good that will be practically, but I'm not sure. But I mean, in certain cases, super channels are useful, like because let's say you have a teleportation circuit, or, you know, like I mean, there are many nice cases where if you work in the super channel framework, like optimization becomes a single SDP rather than, you know, like 2 different SDPs and all like that. So yeah,
I see.
Details. Yeah.
Interesting.
So, are there any further questions from anyone in the audience?
Yeah. Hi, Robert. Maybe I also so I was also considering about the low weight approximation, but my point is mostly about to reconstruct the CPTP map.
Yes.
So maybe I want to consider one specific case. So let's say the CPTP map is some complex quantum algorithms, like the shell algorithms or some FTQC algorithms. So basically, if we get a low weight approximation, we can just reconstruct it by very small additional errors, like by the important sampling, right? So in that sense, I think we can compress we can remove the very high restrictions from the FTQC algorithms to some very simple quantum circuits. Although maybe it will introduce additional error, especially it is about average case, not worst case. But I think it's also okay, right? So like based on the recent quantum device, if we can somehow just decrease the circuit quantum circuit requirements, and to some very simple case, like just the better sampling and the poly operators. And maybe in our case, we can get some very good outputs of the quantum algorithms. I think it's kind of very, yes, I was considering in that direction. So I was curious about your ideas, yes. And yes, by the way, I personally, I suggest using Midjourney instead of DALL-E because Midjourney is kind of,
I've also been playing with Midjourney. No, it's much better. These are old slides from months ago when DALL-E is like the best we have. So it has after a while, these pictures would now look a little bit kind of rusty. So I agree. Yeah, that's an interesting idea that you suggested. Like if we can learn some more, like for example here, because the function we're trying to learn only depends on low weight terms. So perhaps it could be implemented more easily. Although at the moment, I'm not sure how one could do it. And of course, there's also a challenge that one needs to be careful. Is like when you try to do certain things and then you realize that, oh, I could do it with more noisy quantum device or maybe early fault-tolerant quantum computer. Maybe I could also do it classically, right? Like for example, here, the learning was done purely classically and it seems to be kind of good. So one also needs to be careful understanding like what's the role of noisy quantum device or early fault-tolerant quantum computer in the case, like when you try to explore these things. So that I'm not.
I agree with that. Yes.
Okay, so thanks for the nice question and the discussion. So I think we are already like 15 minutes past the regular slot, and it might be getting late for Robert also. So thanks Robert for agreeing to talk, and we look forward to having you again in some future session. Because I think the rate at which you write papers is bigger than the rate at which we read papers. So see you again, and thanks everyone for coming, and
thank you so much. Bye.
We close the session now.